This video lecture 3 mainly deals with important formulas related to design of a leaf spring and what are the variables that are involved in in these particular formulas, and also we'll be solving a problem. So let us start. Now here you can see the first formula. The first formula what you are seeing on the screen is PF. Here the PF is the load acting on the full length leaves. Since already we have discussed in the earlier video lecture, the leaf spring leaves are divided into two groups: full length leaves and graduated leaves. So the load that is taken by the full length leaves can be calculated here by using this particular formula. And also you can see this formula. In this particular formula we are calculating PF by using P. Now what is P? P is nothing but the total load that is acting on the leaf spring. And if you refer the second formula is similar to the first formula, but here we are calculating the load that are acting on the graduated leaves. Okay. And the third one, that is the bending stresses. So bending stresses that are induced in full length leaves can be calculated by using this formula, and bending stresses in graduated leaves can be calculated by using this particular formula number 4. Now if you refer formula number 3 and 4, you will be noticing there is only one change, that is here we are using 18 and here we are using 12, and the rest of the part of that particular formula is same. Okay, the only change what you can find here in this formula number 3 and formula number 4 is here we are using 18 and here we are using 12, and the rest of the part is same. And also in the previous video lecture we have also seen that bending stresses in full length leaf will be 1.5 times of the graduated leaf. So which means bending stresses that are induced in full length leaf will be 50% greater than the bending stresses that are induced in graduated leaves. Once again, let me repeat this. From this, what we can say, bending stresses in full length leaves will be 50% greater. Will be 50% greater than the bending stresses in graduated leaves. Since there is a variation in the stresses, by this we can say there is a variation in the stresses in both the group of leaves, then that could lead to stress concentration and failure may occur. So in order to overcome that, what we'll be doing, we'll be going for a nipping of a leaf spring. So in earlier video lecture also we have discussed, but somehow we'll be again discussing in this video lecture also. Now, in order to balance or in order to equal the bending stresses in both the group of leaves, what we'll be doing, we'll be making the leaves in such a way that the radius of curvature of these two leaves will be different before assembly, or else I can say during fabrication of individual leaf of a leaf spring, they are so fabricated that the radius of curvature of both the group of leaves will be different, and when they are held together or keep in position in a required position, then it will be producing some gap C, and this gap will be this gap will be reduces to zero. This gap will be reduces to zero when a preload is applied. When a pre-initial load is applied, and that particular pre-initial load will be applied by using a U-bolt. Okay, by using a U-bolt. So suppose let us say this is a full length leaves. Leaf here, and this one is a graduated leaf. Now you can see initially there is a gap between these two leaves, and once we apply the initial preload, the gap will become zero. And after becoming zero, or else sorry, once the load is applied, this gap will reduce to zero, and also some pre-stresses are induced in graduated leaves and as well as full length leaf, which will be making the whole assembly of a leaf to subjected to the same bending stresses during maximum load. Okay. Now this particular gap we need to calculate. Why? Because we should know how much gap there should be so that the required amount of stresses, pre-stresses can be developed in graduated leaves. So this gap C can be calculated by using this particular formula. Okay, and PI, that is initial preload, it is offered by using a 2 U-bolts generally. 2 U-bolts will be used to apply this initial preload. And the last formula is, as I have told you, same amount of bending stresses will be developed. And this particular formula deflection we already know. This is to calculate the total deflection that a leaf has been subjected to for a given load. And now here you can see there are two distinct formulae I have written. The reason why I have written this because here you can see I can able to calculate by using PG, and here I can able to calculate by using P. So P is nothing but the external force here. External force or external load. So these two formulas can be used to calculate the deflection. Okay, so this is the way how you can able to solve the problem by using these 8 particular formulas. Okay, so once we have got to know all these 8 formulas, then we can easily able to solve a problem. So let us solve a problem and let us see how we can able to use this particular formula. And also I would like to tell you these formulas are also available in your design data book, but however the notation may varies. Whatever the notation I have used, the same notation may not be there in the data book. So please refer those notation and their nomenclature before you use these formulas. Now let us solve this particular problem. In this particular problem, you can see a semi-elliptical leaf spring is given. Here you can see there is a semi-elliptical leaf spring. Okay, and application is given used for automobile suspension. So generally in a car suspension, we'll be using a semi-elliptical leaf spring, and that too specifically we'll be using in the vehicles in which we want to carry more load. Okay. And you can see here, and what he's saying, automobile suspension consisting of 3 extra full length leaves and 15 graduated leaves. So I can use this and I can able to write the given data. So what is given, I'll be writing given. So full length leaves are represented generally by using NF. So I can write NF is equals to 3. Okay, and graduated leaves are number of graduated leaves are represented in NG, so I can and mg is equals to 15, and this also includes master leaf. Here you can see that including master leaf. Okay, so now here I can write, now from this what I can write total number of leaves is equals to 15 plus 3, and that will be equals to 8. Next is center to center distance between two eyes of a leaf spring. So if you recall back the schematic diagram of a leaf spring, generally a leaf spring will be like this. So from this center to this center point, the distance is given, and that distance is 1 meter. But somehow for design calculation, what we'll be doing, we'll be taking only half of the leaf spring. Okay, that is represented with L, and this one is represented with 2L. So from this what I can write 2L is equals to 1 meter, that can be written as 1000 mm, and that can be further written as L is equals to 500. Why? Because we need only half the length. Since it is symmetric about vertical axis, only half design part is a little bit, so that it will be quite easy for me to write to use the space properly. Next one, the maximum force that can act on the spring is, so maximum force, so the maximum force that can act on the spring is 75 kilonewton. So I can write 2p, total load that is acting on each leaf spring is 75. So for that reason I can write that as 75 into 10 to the power of 3 newtons, and that can be further written as P is equals to 37.5 into 10 to the power of 3 newton. Okay. Next, for each leaf, the ratio of width to thickness ratio is 9:1, and the modulus of elasticity of the 9:1. Here you can see that width to thickness ratio is 9:1. The modulus of elasticity of the leaf spring is 207 or 207,000 207,000 Newton per mm square, and the leaf spring is pre-stressed a way that when the forces is maximum, the stresses induced in all the leaves are same and equals to this one. So from this what I can able to write, I can write B by T is equals to 9:1 or 9 by 1, and from this I can write B is equals to 9 times of T. Okay, and another one information is given, Young's modulus is given, and that is equals to 4. Young's modulus is given as 207 into 10 to the power of 3 Newton per mm square. Okay, and now this will be sigma b, because when maximum load is acting, both the leaves are subjected to same and equal amount of bending stress, and that is given as 450 Newton per mm square. Okay, next what we need to calculate, width and thickness of the leaves, initial nip, and the initial preload required to close the gap C between the extra full length leaf and graduated length leaves. So what I need to calculate, to be calculated, but to be find is, number one is we need to find what is B and what is T, and second one we need to find out what is the value of C, that is initial nip, and third one is what is the pre-load, represented as P. So let us solve this problem. Okay. So let me solve this. So So in the first bit, I'll be calculating B and then D. So for this, what I'll be doing, I'll be calculating sigma B formula. Since sigma B formula is, with the sigma B formula we have seen, you can see from here, sigma B is nothing but, here you can see that. And once again, let me say this formula will be available in your design data book, BT square. Okay, so this can be equals to, let me write that below, 6 into P we have already seen, it is 37.5 into 10 to the power of 3, and L we have calculated 500, N we have calculated 18, you can see here 18 is there, into B, instead of B what I can write 90, make it right P square, and this will be and sigma B value is given, so I'll be writing here 450. So if you equate this and if you solve this, you will be getting T is equals to 11.56 mm, and that will be approximately equals to 12 mm. So once we have calculated T, by using this condition I can able to calculate B. B is equals to 9 times of 12. 9 times of 12 is 108 mm. So like that I can able to solve it. But it is easy. Okay. Now next I will be solving the second bit. In the second bit we need to calculate C. What is C actually? Initial nip. Initial nip is generally represented with C. And what is the formula to calculate initial nip C? Here you can see that it is written here. I can write 2P L cube divided by En BT cube. Okay, so I can able to solve this. So 2 into P is 37.5 into 10 to the power of 3. L is 500 cube divided by E is given 207 into 10 to the power of 3. N is 18. B we have calculated 108 and T is 12. If you solve this, you will be getting the value of C. Take 2 C. So now next last bit, that is the third bit, and in that we need to calculate initial preload, that is represented as Ti. Okay, so Ti can be calculated like this using this formula, and you can see this is the same formula what we have seen earlier. You can see here Pi, and by using this formula and by substituting all the given data like what is Ng, what is Nf, what is P, and all these things, and we can be able to calculate what is the initial force, which means that from this problem here is the following conclusion what we can draw, that you need to make the leaves in such a way that when they are kept together it should produce a gap of 13.48 mm around, and in order to reduce that gap you need to apply a load of pre-load force of 4807.69 Newton. So that should apply that much amount of load when you are initially tightening the U-bolt. So this is how you can able to do. Hope you have got this problem, and also I'll be giving you one additional problem. Please go through that problem and you just try to solve this.